All right, let's go ahead and close this lesson off by talking a little bit about the idea of a reducing sugar. So let me draw a little bit of a line here. Now, monosaccharides, I'll just write monosacs, can be oxidized by very mild reagents, such as, in particular, I should say, iron 3+ and copper 2+. So the sugar is oxidized, okay? They are reducing agents. They are reducing agents. So, reducing agents are the things that are oxidized. They're reducing agents because they reduce the iron and they reduce the copper, but they themselves are oxidized. Very, very important. Okay. As such, they are called reducing sugars. They are called reducing sugars. Again, the carbonyl carbon, the carbonyl C is oxidized to a carboxyl group, to a carboxyl group. The general reaction is as follows. You have R, C, this is the aldehyde, okay? Let's just go ahead and use 2 copper 2+ to 2 copper 1+, and what you end up with is RC. What you end up with is that. So this aldehyde is actually converted to a carboxyl, okay? Because that's available, the free end of the linear form of the sugar. So we call them reducing sugars because they're capable of being oxidized by iron or copper, iron ion and copper ion. As such, we call them reducing sugars because they're reducing agents. That whole oxidation reduction thing, calling them reducing agent, it still confuses me. I just think in terms of oxidation, but they're called reducing sugars. Okay, let's go ahead and draw out the reaction in full form. So let's go ahead and start off with a nice hexose structure like this. Let's go ahead and use our beta form. OH, 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 and then we have CH2OH there. So this is, actually, you know what? I'm going to use, make a little bit of a change. Just for a little slight variation, I'm going to use galactose. Instead of glucose, I'm going to use beta-galactose. So beta-galactose, just for a little bit of variation. So this is beta-galactose. Notice in the glucose, so 1, 2, 3, 4. Galactose is a C4 apimer of glucose. Everything is the same except at the 4th carbon, the hydroxy is on the other side. It's above the ring instead of below the ring. So it's a different conformation, a different actual molecule. So this, now the ring form is going to be in equilibrium with the linear form. So there's going to be some linear form of this sugar that's going to be available. 1, 2, 3, 4, 5. I have 6 carbons. I open it up. I have the aldehyde on top. And of course I have OH here. This time I have 2 OHs on the left. I have this one. Oops. And of course I have my non-chiral carbon, so CH2OH. There we go. So now, once it actually opens up and this end is free, it can react with 2 copper 2+ ions to release 2 copper 1+ ions. And of course now, 1, 2, 3, 4, 5, 6. This is H2OH. I have my carbonyl which has been, my aldehyde has been oxidized now to a carboxylic acid. This hydroxy is on the right, this hydroxy is on the left, this hydroxy is on the left, and this hydroxy is on the right. So what I have here is beta-galactose, ring form. This is also beta-galactose, linear form. This one, galactonate. Remember, gluconate, galactonate, this ON. Just drop the OSE from the galactose, glucose, mannose, add the ON, and either put galactonic acid if this is protonated, or galactonate if it is deprotonated. And that's it. I'll go ahead and write that. Or galactonic acid if protonated. In other words, if this is protonated right up here. If that is protonated. Okay? Now, of course, the aldehyde group must be free in order for this reaction to take place. In order to be oxidized. So the aldehyde has to be free. These are in equilibrium. In solution, yes, it's going to exist mostly in this form, but there's always going to be some of this, available. And once this is actually used up and converted to this, then more of this is going to open up. So this is just an application of Le Chatelier's principle. So a reducing sugar is precisely this. A reducing sugar is a sugar that can actually be oxidized by copper 2+ or iron 3+ to form the corresponding aldonic acid, which itself can actually form a ring again to form that delta lactone that we just mentioned a little bit earlier. Okay, that should just about cover it as far as derivatives is concerned. Thank you for joining us here at Educator.com. Take care. Bye-bye.